Alright, part 7. This is going to be going over chapter 7 and part of 9 with the ions and the ionic bonding. Alright, 64 says, explain how the following elements become an ion. Remember, everybody but the noble gases are not happy with their situation. They want to do something to get the octet. So they're either going to give up or gain electrons, or they're going to do what the covalent guys do. They're going to share electrons to get the octet. Right now we're talking about the ions, so these are the ones who've given up or gained electrons. So now they have an imbalance. They have more or less electrons than their protons, so then they have a charge. So letter A, any group 1 element. Well, group 1 element ends in S1. They have one extra electron out there, so they don't want it. They want to lose it, so there's your answer for letter A. They want to lose one electron, and then that'll give them the octet. Letter B, any element with 6 valence electrons. 6 valence electrons means they're 2 away from 8, so they have to just gain 2. C, nitrogen and phosphorus, you have to find out what group they're in. They're in group 5, or 15 if you go by the other method, and they're going to gain 3 more electrons to get up to the 8. So whatever group number they're in, that's how many valence electrons they have, and then figure out what else they need to get to 8. Letter D, any element with 3 valence electrons. If you have 3, no one's going to give you 5, so you're going to lose 3. E, iron with a Roman numeral 2 in parentheses. That 2 means that's the charge. It's a metal, so it's going to be a cation. That's going to be positive, so it's a positive 2. And then it's going to lose 2 electrons in order to become positive 2. Finally, F, an element whose configuration ends in 5s2, 4d10, 5p5. Now you're looking for valence electrons, which are the electrons in the outermost energy level. So completely ignore this 4d10 here. That's not the highest energy level, the 5 is. So you're going to look at the entire 5th energy level, 5s2, 5p5. The 2 and the 5 is 7, so you have 7 valence electrons. That means you want to gain 1 more to get to the 8. Alright, number 65. 65 is filling out a table so you know the differences between cations and anions. Cations are going to be metals. Remember, you can remember that T in the middle of cation and the T in the middle of the word metal. Cations also are positive. You can remember the T in the middle of the word cation kind of looks like a plus sign or a positive sign. And then finally, how do you become positive? You become positive when you lose electrons. If you don't have as many electrons as you used to, that means you're going to end up with less negatives and therefore more positives. Anions, there's 2 N's in the word anion. One can stand for nonmetal. This N is nonmetal. The other N is negative. Anions are negative nonmetals, and they become negative because they gain electrons. They have more negatives, so now they're negative. Alright, number 66. Number 66 is asking us about parentheses. It says, when are parentheses used in writing formulas for ionic compounds, and then why are Roman numerals used? Well, let's tackle both of these. Parentheses are used when there's more than one polyatomic ion. So for instance, if I'm dealing with magnesium, which makes a +2 charge, and it's bonding with hydroxide, and that's a -1. I want to indicate that there's one magnesium bonding with 2 of these guys, an OH and another OH. If I just write MgOH2 without parentheses, then I'm really telling somebody that it's 1 magnesium, 1 oxygen, and 2 hydrogens. And that's not what I want to imply. I want 1 magnesium, but I want 2 OHs, 2 packages or 2 sets of OH. So I have to put the whole package in parentheses. Whatever you studied goes in parentheses. Let's do another one. What if aluminum is bonding with nitrate? We're going to take the charges, take the 3 and put it down here, take the 1 and put it down here, which you don't need to write, it's an imaginary one. And then you look at this and you want 1 aluminum and then 3 packages of nitrate. We got this 3 out here saying 3 of these guys, 3 sets of nitrate, so you have to put all of nitrate in parentheses. If you don't, it's going to look like 33 oxygens, which you don't want. So put the whole NO3 in parentheses. Okay. Alright, Roman numerals. Roman numerals are used in the name when a metal can make more than one charge. These are your D block guys and under the stair step. These guys, if you see that they're involved in a compound, you should immediately check your reference sheet and see if it's on the list. Because if it's on the list, that means it makes more than one charge and you have to use Roman numerals. For instance, if I had FeO versus Fe2O3. Now I look at this and say, well, I can't just call this iron oxide because I don't know which one I'm talking about. This is iron oxide, that's iron oxide. So which iron is it? In this one, if we uncrisscross our charges, we put a -1 up there and we put a +1 up here. Now before you decide that iron makes a +1 charge, you need to ask yourself, is the nonmetal charge correct? Does oxygen make a -1? And the answer is no. The oxygen makes a -2 all the time. So we double the oxygen, and then we double this one, and over here we're going to write iron 2, because we've doubled it, and then oxide. Now over here, if we uncrisscross the charges, we put a -2 up there, and we put a +3 over here. And then we ask ourselves, is the nonmetal correct? Does oxygen make a -2? And the answer is correct. So that means that this one's correct. So this is going to be iron with a Roman numeral 3 oxide. So now we can tell. If somebody says iron 2 oxide, we know it's this one. If somebody says iron 3 oxide, then we know it's this one.